What is the smallest thing in the universe? Atoms? No. Quarks? Maybe not. Some physicists believe that even quarks might be made of something smaller particles called preons. If that's true, it would mean we still haven't reached the deepest level of reality. So tonight, let's go deeper than atoms, deeper than quarks, and explore the possibility that the universe is built from something even more fundamental. Tonight, we are going to explore one of the deepest mysteries in modern physics. What is the smallest thing that exists in the universe? For centuries, humans have tried to answer this question. Philosophers, scientists, and thinkers have all wondered about the fundamental building blocks of reality. If you take any object around you, a rock, a glass of water, a metal coin, and keep breaking it into smaller and smaller pieces, what do you eventually reach? Is there a final level of matter? Or does the process continue forever? Long ago, ancient philosophers in Greece proposed the idea of something they called the atom. The word itself comes from the Greek word meaning indivisible. According to thinkers like Democritus, matter could not be divided infinitely. Eventually, you would reach tiny particles that could not be cut any further. These particles, they believed, were the ultimate building blocks of reality. For thousands of years, this idea remained purely philosophical. There was no way to observe atoms directly, and no experimental evidence to prove they existed. But the idea was powerful, and it continued to influence scientific thinking for centuries. Then, in the 19th century, scientists began to gather real evidence that atoms might actually exist. Through experiments in chemistry and physics, researchers discovered that matter behaved as if it were made of discrete particles. Chemical reactions always occurred in fixed ratios, suggesting that atoms combined like tiny building blocks. Eventually, the atomic theory became widely accepted. For a time, scientists believed they had finally discovered the smallest units of matter. But the story was far from over. At the end of the 19th century, a physicist named J.J. Thomson made a discovery that changed everything. While studying electrical currents in vacuum tubes, Thomson identified something surprising. Inside atoms, there were even smaller particles. He had discovered the electron. This meant that atoms were not indivisible after all. Instead, they had an internal structure. Soon after, another scientist named Ernest Rutherford conducted a famous experiment using thin sheets of gold foil and beams of alpha particles. The results were astonishing. Most of the particles passed straight through the gold foil, but a small number bounced off at sharp angles. From this experiment, Rutherford concluded that atoms contain a tiny, dense center called the nucleus, surrounded by a cloud of electrons. Later discoveries revealed that the nucleus itself was made of two types of particles, protons and neutrons. For several decades, scientists believed they had finally reached the fundamental level of matter. Electrons, protons, and neutrons appeared to be the true building blocks of everything. But once again, the universe had another surprise waiting. In the 1960s, physicists studying high-energy particle collisions discovered that protons and neutrons were not fundamental particles either. They were made of even smaller components called quarks. This discovery was made possible by powerful particle accelerators and the development of the modern theory of particle physics known as the Standard Model. According to the Standard Model, the universe is built from a small number of fundamental particles. These include quarks, electrons, neutrinos, and several other particles known as bosons, which carry the fundamental forces of nature. Particles such as the electron appear to have no internal structure. They are considered point-like, meaning they behave as if they have no size. Quarks, which form protons and neutrons, are also believed to be fundamental. Experiments at facilities such as the Large Hadron Collider have probed the structure of these particles at extremely small distances. So far, no evidence has been found that quarks or electrons are made of anything smaller. But physics has taught us an important lesson. Every time scientists thought they had reached the final level of matter, they eventually discovered something deeper. Atoms contained electrons. Protons contained quarks. So the question naturally arises, what if quarks themselves are not fundamental? What if there is another hidden layer beneath them? This idea leads us to one of the most fascinating hypotheses in theoretical physics, the idea of preons. Preons are hypothetical particles that some physicists believe could be the true fundamental building blocks of matter. According to this hypothesis, particles that we currently think of as fundamental, quarks, electrons, and other elementary particles, might actually be made of even smaller components. If this idea is correct, the entire standard model might only describe a middle layer of reality. Beneath it could exist an even deeper level of structure. But the Preon hypothesis raises many difficult questions. What would these particles be like? How small would they be? And if they exist, why haven't we detected them yet? To explore these questions, scientists have developed a number of theoretical models that attempt to describe how preons might work. Some of these models suggest that all known particles could be built from just a few types of preons. In this view, quarks and electrons would be similar to molecules, combinations of smaller building blocks bound together by new fundamental forces. But developing such theories is extremely difficult. The energies required to probe structures smaller than quarks may be far beyond the capabilities of current particle accelerators. Even the enormous machines built at places like the CERN may not be powerful enough to reveal this deeper level of reality. Still, the possibility remains fascinating. If preons exist, they could completely transform our understanding of the universe. They might explain why there are so many different particles in the standard model. They might reveal new forces of nature. And they might show us that the structure of matter continues far deeper than we ever imagined. But the Preon hypothesis also faces serious problems. And many physicists today remain skeptical that such particles actually exist. So the question remains open. Have we already discovered the smallest pieces of reality, or is there still another hidden layer waiting to be revealed? To understand why scientists even began thinking about particles smaller than quarks, we need to look more closely at the structure of the standard model. At first glance, the standard model is one of the greatest successes in the history of science. It explains an enormous range of experimental results with remarkable precision. Predictions made by this theory have been tested countless times in laboratories around the world, often matching experimental measurements with incredible accuracy. One famous example is the discovery of the Higgs boson. For decades, physicists believed that this particle must exist in order to explain why other particles of mass. In 2012, experiments at the Large Hadron Collider finally confirmed its existence. The discovery was considered a historic triumph for modern physics. Yet despite its success, the standard model also contains several deep mysteries. One of the most puzzling aspects of the theory is simply the number of particles it includes. If you open a textbook on particle physics, you will find an entire zoo of particles. There are 6 types of quarks, 6 types of leptons, multiple force-carrying particles known as gauge bosons, and several additional particles associated with the Higgs field. In total, the standard model includes more than a dozen fundamental particles, each with its own mass, charge, and quantum properties. But this raises an important question. Why exactly these particles? Why 6 quarks instead of 2, or 4, or 10? Why do their masses vary so dramatically? For example, the top quark is about 340,000 times heavier than the electron. Yet the standard model does not explain why these numbers exist. It simply describes them. This situation makes some physicists uncomfortable. In many areas of science, when we encounter a large number of seemingly arbitrary parameters, it often suggests that we are missing a deeper level of explanation. Consider chemistry as an analogy. Before the discovery of atoms, scientists knew that substances combined in fixed ratios, but they could not explain why. The answer only became clear when the atomic structure of matter was understood. Similarly, some physicists suspect that the standard model might be like an incomplete map. It works extremely well for describing what we observe, but it may not reveal the deepest structure of reality. This is where the idea of preons becomes interesting. In many preon models, the large number of particles in the standard model could be explained as combinations of a much smaller set of fundamental building blocks. In other words, quarks and leptons might not be fundamental at all. They could be composite particles, built from smaller components. This would be similar to how protons and neutrons are made from quarks, and how atoms are made from protons, neutrons, and electrons. If this idea were correct, the complicated particle zoo of the standard model might reduce to a much simpler set of underlying particles. Some early preon theories proposed that all known particles could be built from just 2 or 3 types of preons. These preons would combine in different ways to form quarks, electrons, and other particles. In this sense, the standard model particles might resemble different arrangements of the same basic building blocks, much like letters forming different words. However, creating a consistent theory of preons is not easy. One of the biggest challenges is explaining how these hypothetical particles could be bound together. Inside protons and neutrons, quarks are held together by the strong nuclear force, which is described by a theory called quantum chromodynamics. This force is incredibly powerful, and it becomes stronger as quarks try to move apart. But if quarks themselves were made of preons, an even stronger force would likely be required to hold those preons together. Physicists sometimes refer to this hypothetical interaction as a hypercolor force. Such a force would operate at extremely tiny distances, far smaller than anything currently observable, and detecting it experimentally would require particle collisions at energies far beyond what our current technology can achieve. Another difficulty arises when scientists try to calculate the predicted masses of composite particles made from preons. In many theoretical models, the masses of these composite particles turn out to be extremely large, far larger than the masses we actually observe for quarks and electrons. This creates a serious problem. If quarks were made of smaller components, we might expect them to behave differently in high-energy experiments. But so far, all experimental evidence suggests that quarks behave as point-like particles, even at incredibly small scales. Experiments at facilities such as the CERN have probed distances thousands of times smaller than the size of a proton. Yet no internal structure of quarks has been detected. Of course, this does not completely rule out the possibility that quarks have deeper structure. It may simply mean that the scale of that structure is far beyond our current experimental reach. If preons exist, they could be associated with energies trillions of times higher than anything we can produce today. And that leads to another fascinating possibility. The deepest structure of matter might only become visible under conditions similar to those that existed in the very early universe. Just moments after the Big Bang, temperatures and energies were unimaginably high. Under those extreme conditions, the fundamental particles we see today may not have existed in their current form. Instead, they might have emerged from a deeper layer of physics, possibly involving particles like preons. If that idea is correct, studying the earliest moments of the universe might reveal clues about the deepest level of matter. And that possibility has inspired many physicists to continue exploring these theories, even though experimental evidence remains elusive. Because history has shown us something remarkable. Every time scientists thought they had reached the ultimate building blocks of nature, they eventually discovered something smaller hiding beneath. But even though the idea of preons is fascinating, scientists must be extremely careful when proposing new layers of reality. In physics, a theory is not judged only by how interesting it sounds. It must also obey the strict mathematical rules that describe how the universe behaves. And this is where the Preon Hypothesis begins to encounter some of its most difficult challenges. One of the most important principles in modern physics is known as quantum field theory. According to this framework, the fundamental particles we observe are not tiny solid objects like miniature billiard balls. Instead, they are excitations of underlying fields that exist throughout space. For example, the particle we call the electron is actually a vibration of something known as the electron field. Similarly, quarks arise from their own quantum fields, and force-carrying particles such as photons arise from the electromagnetic field. Within the framework of the Standard Model, these fields are considered fundamental. They are not made of smaller parts. Instead, they represent the most basic level of physical reality that we currently understand. So if preons exist, they would require a deeper theory that goes beyond the Standard Model. And such a theory must satisfy many very strict conditions. For instance, it must correctly reproduce all of the particle properties that experiments have already measured with extreme precision. This includes properties such as particle masses, electric charges, and quantum numbers. One of the most famous results in particle physics that creates difficulties for preon models is known as the 't Hooft anomaly matching condition, discovered by the physicist Gerard 't Hooft. This mathematical rule places very strong constraints on how composite particles can behave. In simple terms, if quarks and leptons were made of smaller particles, the mathematical symmetries of the theory must still match the symmetries observed in experiments. But constructing a consistent preon model that satisfies these constraints has proven extremely difficult. Many early preon theories from the 1970s and 1980s eventually failed these mathematical tests. As a result, interest in preon models declined for several decades. However, the idea never completely disappeared. Some modern physicists believe that deeper structures may still exist, but in forms very different from the original preon proposals. For example, certain theories suggest that the fundamental particles might emerge from topological structures or more abstract mathematical objects. Others explore the possibility that particles arise from tiny vibrating strings, as proposed by string theory. In this picture, quarks, electrons, and other particles are not made of smaller point-like particles at all. Instead, they are different vibration modes of extremely small one-dimensional strings. If string theory is correct, the universe might contain additional hidden spatial dimensions beyond the familiar 3 dimensions of space. These extra dimensions could be curled up at incredibly small scales, far smaller than atoms or even quarks. The vibrations of strings within these hidden dimensions would determine the properties of particles we observe. In that sense, the ultimate structure of matter might not involve smaller particles at all. Instead, it could involve deeper geometric or mathematical structures. Another fascinating possibility comes from the idea that spacetime itself might not be fundamental. Some physicists believe that spacetime may emerge from more basic quantum information processes. In certain theoretical models, the fabric of reality might resemble a vast network of interacting bits of information, something like a cosmic quantum computer. Within such a framework, particles might appear as stable patterns of information within this deeper structure. Ideas like these show that the search for the ultimate building blocks of nature is far from over. The question of whether quarks and electrons are truly fundamental remains open. Future discoveries may reveal entirely new layers of physics that we cannot yet imagine. New experiments could push the boundaries of our knowledge to smaller and smaller scales. The next generation of particle accelerators may explore energies far beyond those reached by the Large Hadron Collider, and observations of the early universe, including precise measurements of the cosmic background radiation left over from the Big Bang, may also provide clues about the deeper structure of matter, because the earliest moments of the universe may have revealed physical laws that are hidden from us today. In the end, the story of physics is a story of layers. Atoms were once believed to be the smallest things that exist. Then we discovered electrons, protons, and neutrons, then quarks. Each discovery revealed that the universe is more complex and more beautiful than we had imagined. So when we ask whether preons exist, we are really asking a deeper question. Have we finally reached the bottom layer of reality, or is there still another hidden level waiting to be discovered? Perhaps somewhere far beyond the limits of our current experiments, the true foundations of the universe are still waiting quietly to be revealed.